Hi, my name is Chris Maxwell. I'll be presenting this webinar on the hidden costs of condition-based maintenance. I'm a senior reliability engineer here at Quanterion. We have a packed slide deck, so let's get into it. The goal is we need to get to slide 5 quickly, then slide 10, and then slide 19. Everything else in between is kind of support information that you can read at your leisure when you get the slide deck afterwards, but we're trying to keep this fast. We've got all the details in the slides, but we'll try to keep to the high points to get through it. Quanterion is based in Utica, New York. We provide reliability data, reliability analysis services. We generate the 217 plus empirical model for electronics parts. We are the creator of the NPRD, EPRD, and FMD data sets, which are generally recognized as the largest data sets of surrogate data in the world. This is our agenda. This is sort of a pun of a question that I asked myself about condition-based maintenance, as in comparing a part failure to a tree falling. One of the main things is trees generally fall without warning. Condition-based maintenance is generally predicated on having warning, which is usually conceptualized as the PF curve. Some failures have warning, some failures don't. Sometimes you'll stand a long time listening, and you might not know until it's already failed. A little instruction on how to use these slides. Generally, there's buzzwords all through these slides. You can get details by searching on the buzzwords and get the details for yourself. We're going to try to stay high level and conceptual. This slide has to do with some of the actual Internet of Things implementation of condition-based monitoring, which is part of condition-based maintenance. This is a topic for another webinar, actually, but we just needed to mention it. General concepts that I'm using. These are some definitions of some of the buzzwords that are loaded into the slides. PF curve and the DIPF curve are heavily used in condition-based maintenance. We'll talk about some of these other curves. Bathtub curves are classic reliability, is a classic reliability concept, often over-applied, as in generally people always talk about the bathtub curve, but there was a study done by United Airlines that classified what they called the A through F versions of the curves, which is the actual classic bathtub is a relatively low percentage of the time. Stress and strength interference. The more we act on these curves, the more they change. Sometimes you don't measure a bathtub curve for a parts lifetime relationship because you're already replacing it. You're not letting it get to wear out. That's especially true in the aircraft industry. They're not going to be leaving bearings in a turbine or a turbofan engine just to see how long it is before it wears out or breaks. They're getting them out of there before they get to the wear out portion. To the owners of assets, I get it. I may be a reliability engineer, but I also own some assets. This is my barn. We run things to failure sometimes. So I'm just saying sometimes I realize I'm a hypocrite, as all reliability engineers are. So this slide we want to spend some time on. This is sort of the meat of what we're talking about here, right? I call them nuances, but they're hidden costs, okay? Sensors that you use to do your condition-based monitoring, they can bring their own unique and new and novel to you failure modes to the table. You may be monitoring some refractory process or some high temperature rotating machinery. Your sensors might not be immune to those environments that you're using them in, right? You know, your process or your machinery may be perfectly happy with 200 or 400 degrees Celsius. The electronic sensor that you're putting in there may not really like that, or the insulation on the wires may not like that. Or there may be copious amounts of electromagnetic interference being generated within your plant that your sensors, if they're wireless, need to be immune to. You also have some novel cyber vulnerabilities nowadays, especially with Internet of Things. Your sensor data is it can be literally wirelessly transmitted to places. Hopefully, if you hire a monitoring service or a condition-based maintenance monitoring service that's monitoring and interpreting your data, they need to be secure, okay? And you will develop a data history, but how much does it cost to develop that data history? It generally should be worth the cost. Is it secure? Is it anonymous? Is it for sale? The other question that we're going to get into is you may not have that data history when you're in the design phase of your plant or your process or your system, and you need to be able to at least budget for typical failure rates from the beginning. I have a little note to myself on the side relative to data fatigue. You can get data fatigue from false alarms. If you get false alarms all the time, if your machinery is crying wolf, you generally don't listen anymore. If you get no alarms, you also get data fatigue. You stop watching. One point that I didn't bring up is that for any given component, different failure modes may have different warnings and PF intervals, which also gets to their one of the uses of, say, surrogate data is surrogate data can help you to classify the failure modes during, say, a design phase. When you're doing FMEA, you might not know which failure modes to consider, okay? And so the magic buzzword there is taxonomy, right? Our EPRD and NPRD use plain English taxonomy, which is documented in the failure mode distributions. Certain industries have their own taxonomies. ISO has a standard. IAEA tech docs have charts of failure modes. NUREG and ORITA both have charts for failure modes. Usually it's either a 2 or 3 part code, almost like a phone number, where there will be a 3-letter code for the part type, then a dash or a space, and then a 3-letter code for the failure. For instance, in NUREG, you would have, say, a manually operated valve, which might be, I think the code for that might be MOV, and then dash ELL is external leak large, ILL is internal leak large, or SOP might be like spurious operation. So surrogate data can help you to figure out what failure modes you want to classify or consider in your DIPF curves or your PF curves. This false alarms and maintenance fire drills, this applies to every type of maintenance. If your condition-based maintenance is generating a lot of false alarms, or if your P point on your PF or DIPF curve is too far to the left and you're replacing too soon, you introduce yourself to the new failures that can be brought about by maintenance procedures. Lots of times, companies will experience a forced outage right after a planned or predicted or condition-based maintenance procedure. Every time somebody takes your stuff apart, every time they work on it, every time they put it back together, they can cause new and novel failure modes. So let's talk about solutions. At the beginning of your process design or your part design or your system design, all I'm going to say here is an ounce of diligence is worth a pound of monitoring, okay? It's similar to mantras that are talked about, reliability engineers. You can't screen reliability into a part. You can't, your metrics won't make things reliable, but it's true. An ounce of diligence is worth a pound of monitoring. To improve your P point on your curves, physics of failure models can help, right? If you know the physics behind the failures, the mechanisms, POF models help you to refine your PF curves They help you to implement corrective actions. They help you to refine your design features and your maintenance features to lengthen the life of your parts in your systems. We're going to talk a few slides about surrogate data. We're going to sit on that for a couple of minutes. Surrogate data is generally interval data. In our EPRD and NPRD systems or sets of data are surrogate data. And generally it's used for budgeting and it's used when you don't have a data history yet. Okay. The main point here is surrogate data can help you to budget. It can also help you to prevent being too lean. Okay. This is our story of surrogate data. Like I said, the NPRD, EPRD, and FMD are generally considered to be the largest data sets in the world. There are other sources of surrogate data, which if the slide changes, there we go. There are other sources of surrogate data, NUREG, IEA, or RITA, that are industry specific. And I have a few notes in here about the theorems and the assumptions that go with surrogate data. Empirical models, we do have an empirical model ourselves generated for electric parts, electronic parts, or EEE type parts. There's also the Classic Mill Handbook 217, NSWC, Naval Surface Warfare Center for mechanical parts, FIDES, Telcordia. There are many different empirical models that can generate point estimates similar in utility to surrogate data. Stress strength interference models can be generated by, say, a finite element analysis or distribution of strength or stresses on your parts. Might be the only method available to model or budget if you don't have data history yet. So reliability growth through condition-based maintenance. This is where we're getting to, sort of the happy ending, if you will. If you apply all of those previous processes to help, you can evolve away from statistical assumptions and let the data guide you. You can get to the Goldilocks level of lean for both your maintenance and sparing, okay? We do have one question that we have a little time to cover. It says, sorry if out of subject of the webinar, how can we identify the interval of maintenance tasks for new development products, which considered there's no similar benchmark? What I would suggest there is you would want to break the interval of maintenance tasks. I'm assuming it's for a process or a system or a design. You would need to break that process, system, or design down into components. And then if it's new to you, if you don't have data on it, your own field data, that's why we covered surrogate data so much. Surrogate data serves as a surrogate or a substitute for your own data. You can go and look up the failure rates of different components and budget for those typical failure rates. The detailed answer there is if you are considering using our own data sets, Quantrion's data sets, NPRD and EPRD, is you can go to our website and go to the product pages for them and click on the part descriptors. Am I saying that right, Deb? Part descriptors. Click on that and you can see a PDF file of every type of part or component that's covered in our data set. There's no commitment there. You don't have to buy anything. You don't have to register for anything. You can just look at that PDF and it'll tell you what parts we have failure rate data on. I actually made a LinkedIn post about that a couple of weeks ago that has some pictures of how you can get there. But generally, that's how you would establish a benchmark, is if you don't have your own field data, you would have to get some surrogate data or do testing to generate a benchmark at the beginning of a design of a process or system. I would like to express my appreciation and thanks for 15 minutes of your time to listen to the webinar. We are doing a Reliability 201 reliability analysis and Weibull analysis training in Albuquerque in September. In November, we're offering Reliability 101 and Software FMEA training. These are open trainings. The roads database is going through a price increase on September 2. It's still available at the current subscription price of $700. We also do custom consulting. We can take emails if you have specific questions at reliability@quantrian.com, or you can contact us through our website. Thank you so much.